Okay, so with the continuation of our last class, we'll study some new contents which is as per the syllabus. So this is on CMOS SR latches. So SR means the set and the set that we generally call as CMOS SR latches and flip-flops. So, as you know, if you can study it in digital electronics, so a flip-flop is a logic circuit that involving feedback. Okay, so the that means the output of the gate drives its input, and primarily via other gates. Okay, so that is basically the logic circuit involving feedback, and the output of the gate it drives its input primarily to other gates. So flip-flops are the basics of digital memory. The SR that we generally call that is abbreviated as SR. So SR means set reset. So this SR flip-flop is basic type of flip-flops. So that is actually we can consider. Okay. So you know these things maybe in the digital electronics. So just a quick brush up so that you can get an idea. Okay. So basically flip-flop is a logic circuit and that involves feedback, and the output of the gate drives its input primarily via other gates. Okay. So, if you can know the difference between combinational and sequential circuits, so the main thing is that the sequential circuits, as you know, it can remember the previous states of its input, and that use them to determine the output of logic states. Okay, so that actually sequential circuit. But in that cases, the combinational circuit, there is no such memory elements, so that make it different from the combinational circuit. So combinational circuit we don't have any memory element, whereas in sequential circuits we have that memory elements. Okay. So if you can just can find the difference between this combination and sequential circuits, we can determine accordingly. Now, basically, the output of that, or more precisely, the logical output of the combinational circuit at any time depends on the logic state of the inputs at that instant of time. Okay, so that means what is the logical output of the combinational circuit at any time, that depends upon the logic state of the input at that same instant. Okay, hence the output logic state is a function of the current logic state of the input. Okay, so that actually the main thing. But in sequential circuit, if you take into consideration the sequential circuit, the logic state of the output depends on the current logic state of the input and the logic state of the input at previous time. Therefore, a new variable, the time that intervenes. So that means if you can think in that way, the sequential circuit can remember the previous states of the input and can use them to determine the output of the logic state. Okay, so as you know, the flip-flop is one of the essential sequential devices. So the main thing is that in sequential circuit, if we take into consideration of the logic state of the output, that mainly depends on the logic state of the input. That means the current logic state of the input and uh, and the logic state of the input at previous times. Okay, but it is not so in case of combinational circuit. Now, in combinational circuits, the output at any time depends upon the input state or the logic state of the input at that instant of time. Okay, so the output of logic state is a function of the current logic state at the input. Now, when we take into consideration, we need to understand the clock pulses train. Okay, so this is, if you can see, this is the train of clock pulse or clock pulse train, which you can see. So you can say this is one period of the clock pulse. So start from here to here up to t, then here to here up to 2t. Like this, it is actually so and so forth. Okay, and this is our which you can say pulse width, that we call it TP. Okay, now this TP pulse width is very less than our that period T. Okay, where T is the period. Period means to take one cycle, the time period which is take, that is really our period. Now the pulse width, if you can see, so this pulse width TP is very less than our period. Okay, so the system clock is a pulse of train of period t, as you can see here. This figure 1, as you can see. Okay. And the pulse width is actually TP. Oftentimes, it is so that the clock signal has a duty cycle of 50%. That means uh, the pulse width is half of the clock period. But however, if you can see, the clock waveform in figure 1 has a pulse width much smaller than the clock period. Okay, so that we will discuss in below consideration. Now, this particular type of clock can help us to create a useful memory elements. Now, the clock signal is usually connected to several different blocks within the digital systems, and that allowing us to operate them synchronously. And the transition of the binary value that that we also call it logic state in such a system occurs synchronously. That means that can change at the state particular the portion of the clock waveform. Okay. Now, when we analyze the sequence of the system, the output values corresponding to the consecutive intervals time, usually denoted as, if you can see here, like Q1, Q2, Q3, Qn, like this. So it is all about analyzing the sequential system. And when we analyze the sequential system, the output value corresponding to the consecutive interval of time t is usually like this. So here I'm denoting as Q1, Q2, Q3, Qn, like this. Now, this is the if we take an example of storing one bit of information. Okay, so how it can be so. Okay, if you can see here, there are I'm taking an example. So if you can see, there are two NOT gates are here. So two NOT gates are, one is N1 and is N2. And if you can see the figure, there are two inputs A1 and A2, and the output is Q and Q bar. Now, if you can see, well, okay, one output if you can queue, but here the input A1 is connected to the output here, and the whatever the output we get from this N1 NOT gate, that is connected to the input of the second NOT gate. Okay. Similarly, the output of the second NOT gate is connected to the input of the first NOT gate. Okay. So, so this is actually the way. So if you can see, if we, let's say this A1 is logic 0. Okay. So its output will be logic 1, and this logic 1 is now given to the input here. So the A2 will be 1, and this logic 1 is will be again 0. Okay, and again this 0 is connected to here, connected to the first input of the NOT gate. So like this way, if you can see, the elementary digital gates that can be implemented to form memory elements that can be used to store the previous logic state of the input in a sequential circuit. Now, this is the figure 2 that we is shown here. This very straightforward way, or the most lucid way to illustrate the digital memory, that is cross coupling of two NOT circuits, N1 and N2. Okay, two NOT circuits, N1 and N2. Now, connecting each gate's output to other gate's input, we can get a feedback combination commonly referred to as latch. Now, this is actually concept where the latch concept is coming into feature. Then, when we connect each gate's output to other gate's input, we can get a feedback combination that we commonly refer to it as latch. Now, the latch is actually a memory element that is characterized by having only two stable logical states at its output, and the circuit can remain either state. That is, here it is logic can be logic 1, or it can be logic Q, will be logic 0. Anything, any logic state can be taken into consideration. So it can be logic 1 or can be logic 0. So it is indefinitely acting as one bit memory. And the latch actually a bistable circuit with two complementary outputs. And since the information is locked, or last. Okay, so that in place of it is actually considered to be latch. So you can think it as a latch is a memory element characterized by having two stable logical states. Okay, and and we get a feedback combination, and that we commonly refer to it as latch. Okay, so if you can see here, as I already mentioned here, so if the output of N1, okay, if the output of N1 in figure 2 is logic 1, the input of N2 is also logic 1. Okay, if you can see here, if the output of this first NOT gate, that is N1, is logic 1, then the output of N2 is also logic 1. Then the output of N2, if Q bar that we call it, this Q complement, this Q and Q complement is 0, then the output of N1 is also 0. Finally, the output of N1 is also that is Q is equal to logic 1, which matches our initial assumption. Okay. So likewise, other possible state we can think Q is equal to 0 or Q is equal to 1. Okay. Now the interconnection prevents having the same logic state in both the outputs simultaneously. Okay, so this is a example, or you can say the illustration, which I want to give you, that how the one bit information can be stored. Okay, so that is actually the illustration behind the storing of one bit of information. Okay, I hope this is clear to everyone. Now, this is actually SR latch. That is SR means the uh, set reset latch that we call it. Okay, so this is a figure which you can see here. Set reset latch with NAND gate. So if you have a NAND gate, so S at R, and here not one NOT gate N3, another NOT gate N4, and this output is connected to this NAND gate, and we have output Q, and this output whatever we get at the from N1, that is connected to the input of this NAND gate N2, and this N4 NOT gate output is connected to the input of N2, and finally we got the output here Q bar. So Q and Q complement, so these are two actually our output of this set reset, or you can say SR latch with NAND gate. Okay, so let's say if the question is asked with SR latch NAND gates, you have to draw like this. Okay, now the we need to develop a mechanism to trigger the latch that is shown in figure 2, which we have already here. You have to shown in the figure 2 and make it a chain state. This is achieved by SR latch, as we can see in this figure 3. Okay. So if you want to develop a mechanism to trigger the latch, which you have shown in figure 2, okay, here in figure 2, and make it a chain state, then this is achieved by our set reset latch. Otherwise, this is called SR latch that is shown in this figure. Okay. Now this SR latch is created by cross coupling of two NAND gates. If you can see here, this is a cross coupling of the two NAND gate. That means because the output of the first NAND gate is connected to the input of the second NAND gate, and the output of the second NAND gate is connected to the input of the first NAND gate. So this is actually the cross coupling of the two NAND gates. And we can see here that how the SR latch allows us to store one bit of information. Now, if you can see here, to store a specific state, let's say Q is equal to logic 1, or let's say Q complement is equal to logic 0 in the latch, we should apply appropriate value to the S and R inputs that shown in this figure here. Okay. So that means we have to apply a proper values to the S and R inputs here that we can see. Okay. Now figure 3 shows the state of the input and output when S is equal to logic 1 and R is equal to logic 0. We set the latch output to the logic 1 state. Okay. Now the S terminal, which you can see here, the S terminal is the set or preset input. And the latch is set when the this q, if you can see here, this q is equal to logic 1 and q complement will be logic 0. Similarly, choosing s is equal to logic 0 and r is equal to logic 1. So first we have discussed C, s is equal to logic 0, r is equal to s is equal to logic 1 and r is equal to logic 0. But here in the second case, we have chosen s is equal to logic 0 and r is equal to logic 1, enters a logic 0 into the memory. And the r terminals is reset or clear input. Okay. And this is actually the SR latch truth table. Okay. So this is actually SR latch truth table, and this is S, this is R, this is Qn and Qn plus one, and what are the means the comment which you can think. So that is considered accordingly. So in this cases there is no change of state. In this case there is output is equal to 0. In this case output is equal to 1, and in that cases it is not allowed. Okay. Now this Qn and Qn plus 1, that is nothing but Qn is the current state. Okay, Qn is the current state of the output at that instant of applying the applying the input combination, and Qn plus one is the next state of the output takes after the applying a given combination to the input. Okay, so Qn is basically the state of output at that instant of applying input combination. Okay, that you should remember, and Qn plus one is the next state of the output that takes after applying given combination to the input. Now the inputs S is equal to logic 0 and R is equal to logic 0 lead to an unknown state, that is Q and plus 1, could be either logic 1 or logic 0. Okay, it can be logic 1, logic 0. With this combination of input, the output actually does not change. That is, the next state of the output is logic 0 if it were logic 0 and logic 1, and if it were logic 1 in that case. Okay, now in this case, the latch remembered its previous state. Okay, if you can see here, the latch remembers its previous state. Now, with s is equal to logic 0 and r is equal to logic 1, s is equal to logic 0 and r is equal to logic 1. Okay, the output goes to the logic 0 regardless of whether it was in logic 0 or logic 1. So, this combination, when s is equal to 0 and r is equal to 1, it will be it will be logic 0. It will be, you can say, the logic 0 or logic 1. Similarly, with s is equal to logic 1 and r is equal to logic 0, the output goes to logic 1 regardless of whether it was in logic 0 or logic 1. Okay, and the last combination, that is actually s is equal to logic 1 and r is equal to logic 1, is not allowed, because it produces a state of interminacy that must be avoided. The set on reset inputs in the SR latch cannot be logic 1 simultaneously. Now, based on the discussion that we have just now we had, so that we can summarize in the truth table, and this truth table, as you can see here, this is the summary of the truth table of SR latch. Okay, so I hope this is clear to everyone. So remember, when this SR latch is given, is asked with the NAND gate, you have to draw like this, and this is the truth table of the SR latch, and this is the summary of the truth table of SR latch. Okay, so you have to explain it like this. Now this is actually the logic symbol of a set and reset latch. Okay, so here. S, and this is R, this is Q and Q complement. So this is the logic symbol for set and reset latch. Okay. So very important thing is that when you explain the things, so you need to explain in a different combination of what actually different combination of S and R, because S and R can be 0 0 0 1 1 0 1 1. So like this. So similarly, similarly, the input, uh, that we have s is equal to 0, logic 0 or logic 1, so that can lead to unknown state that I have already discussed, that is qn plus 1. So either it will be logic 1 or logic 0. Now with this combination of input, the output does not change. That is, the next state of the output is logic 0 if it was logic 0 and logic 1, and if it was logic 1. Okay. Now in this cases, the latch remember the previous state. Okay. So just to once again, I the the illustration which I want to make, and with similarly for s is equal to logic 0 and r is equal to logic 1, the output goes to 0 regardless of whether it was in logic 0 or logic 1. Okay. Similarly, with s is equal to logic 1 and r is equal to logic 0, the output goes to logic 1 regardless of whether it was in logic 0 or logic 1. Okay. So this come you have to remember always. So 0 0, this qn, 0 1 0 1 0 1, and the combination 1 1 is not allowed. Okay. This is not allowed because it produces a state of interminacy, because that produces, and that must be avoided, and the set and reset inputs in the SR latch cannot be logic 1 simultaneously. Okay, and this is the summary of the truth table of the SR latch. Okay, so this is actually the logic symbol for set reset latch. Okay, so whatever we have discussed, that is with respect to NAND gate. Okay, this is with respect to NAND gate which you have seen here. So set reset latch with NAND gate. Let's say if we want to make it with NOR gate, then how it can be? So it will be like this. So this is with respect to SR latch, which is achieved by NOR gate. Okay, if you can see here, so we have a NOT gate here. We have a NOT gate here. So the input is S. Here the input is R, and one output of the this NOT gate is given to the input of this NOR gate. Okay, and we got the output Q, and one input of this NOR gate is given to the output of the second NOR gate. Okay, and similarly, the whatever the output we get at the first NOR gate, the output of the first NOR gate, and that output is connected to the input of the second NOR gate. Okay, so if you can see here, these are cross linked with each other. Okay, just like if you can see in the NAND gate, we have that is uh, cross coupling of the two NAND gates. Similarly, there is a cross coupling of the NOR gate also. So main thing is that the output of the fast NOR gate is connected to the input of the second NOR gate. Similarly, the output of the second NOR gate is connected to the input of the first NOR gate. Okay, and this is R. This is the R NOR gate, and this is connected to the input of the NOR gate. And finally, we got this output Q and Q complement. Okay. So this is the SR latch which is achieved by NOR gate. Okay. Okay. So then we'll discuss about the clocked SR flip flop. So what is this clocked SR flip flop? Now clocked flip flop is one improvement of the basic latch. Okay. This is one improvement from the basic latch. So in order to implement the sequential systems, we need to able to set or reset the output of the memory element in synchronism with the clock pulse. Okay. Now in the case of clocked SR flip-flop, the clock signal similar to that shown that in the figure 1. In the figure 1, uh, this one, the figure 1 which I have discussed here. So in the figure 1, it used to reset or set or reset the output of the appropriate moment. Now with the clocked SR flip-flop, the output change state during the brief period of time that the clock is logic high. Okay. Now this is actually clocked SR flip-flop. Okay. So if you can see here, so this is there are four NAND gates are here. So this is N3. This is input is S. This N4 another NAND gate. So this is our clock signal. We have to give it here. So they commonly abbreviate CK. This is S and this is R. Now this output of this N3, this output of this N3 is connected to the input of N1 here, another NAND gate, and this is actually B1, and this input of this other NAND gate is connected to the output of this N2. Okay, the N2 is the another NAND gate. Similarly, whatever the output we get from the N1, the first the one NAND gate N1, so that is connected to the input of the next NAND gate. And similarly, we get this output Q and Q complement. Okay, now this is actually the control gates and latch. Okay, so this is how this clocked SR flip flop is actually designed. Okay, this is within this NAND gate. Okay, so again, I'm once again a revision. So clock flip flop is basically the improvisation from the basic latch. Okay, now in order to implement sequential systems, we need to be able to set or reset the output of the memory element in synchronism with the clock pulse. Okay, now in the case of clocked SR flip flop, a clock signal is similar to that this clock signal. Okay, this clock signal which you have seen here, that means the period of this is the period of t, and the clock pulse of period of t, and the pulse width of tp, and where the pulse width is very very less than the period of this clock pulse. So this kind of clock pulse train we have to apply. Okay, we have to apply, and that is used to set or reset the output of the appropriate moments. Okay, now with the clock SR flip flop, this output changes state during the beat period of time, that is clock is at logic high. Okay, so okay, so we'll continue with our next session in the next class today at 3:45 p.m.